So I'm going to be talking about some inverse methods that I've been developing that use geomechanical data to try to solve for some of the parameters that control poroelastic processes. So the idea is to use that to be able to monitor and to do site assessment and model calibration in a carbon sequestration project. And so as we're injecting CO2 into a formation, we start getting pressure buildup around the injection well. So we start getting elastic deformation. And so that causes changes in the stress field that we can measure either from inside of the well that we're injecting into or from some other observation well nearby. And so we've been developing some instruments that can measure that kind of data. So this is the Tilt X that one of my professors has been developing. So this measures axial and tilting strains. And this is the 5DX. So this measures 3 components of deformation and 2 components of shear strain. And so part of this project has been improving those instruments using fiber optics. And so my part of the project is taking that data, so it's sensitive to things like the hydrogeology of the area and also to the mechanical parameters that are controlling the poroelastic processes, and also the model geometry. And so I've been developing a set of inverse methods that we can use to try to interpret that data and try to estimate some of these parameters. So the forward model that we're inverting is a 3-layer system. So we have a 1 kilometer thick caprock layer that's impermeable and a 100-meter formation layer that we're injecting into. And so we start injecting CO2 into the formation, and so CO2 starts moving out into the formation pretty quickly because it's permeable. And then it starts moving or diffusing up into the caprock much slower because it's so impermeable. And so that diffusive front we should never be able to measure from up in the caprock. However, because we have this buildup of pressure around the injection well, we'll start to get elastic deformation that starts pushing up into the caprock. And then we get elastic deformation of the caprock as well. And so that's a mechanical signal, so it's not limited by the permeability of the caprock. And so that just moves at the speed of sound, and we can measure it as soon as it happens. And so if we put a well into the formation, then we can get data that's sensitive to a lot of the formation parameters. And because the two are coupled, if we put a well even into the shallow caprock, which is a lot cheaper to do, then we can get data that's still sensitive to both the caprock properties and the formation properties. And so we have this numerical forward model that first we pass in a set of true parameter values. Then we run that, and we get a set of synthetic geomechanical signals. And so we add some Gaussian noise to that to represent measurement error. And alternatively, we would have, in the future, we'll have actual measured data. For now, we're using synthetic data to make sure the method works. So we have our set of either measured or synthetic data, and we have a set of prior models that describe what we know about the parameters in general. And so we can use those models to generate a set of parameter estimates. And so we can pass in any number of those into our numerical model. So it's designed to be distributed, so we can pass in as many models as we want and run them on as many computational nodes as we can get our hands on the supercomputer. And so we can use that to generate a set of predicted geomechanical signals and compare them to either our measured or our synthetic data. Then we have a measure of the error associated with each of these models. And so then we use that error to update our knowledge about the parameters and start building updated estimate of our parameters. So the tricky part is when we're using our errors to update what we know about the model and how we're generating the next set of models. And so we use a couple of different methods to do that. And so one is, the simplest is just Monte Carlo, which just uses our initial prior model to keep on generating estimates. And then we also use a sparsest point method. So we find the sparsest point in the parameter space and estimate or run that run that point in the parameter space. And so the two of those allow us to be sure that we're exploring the whole parameter space really thoroughly and we're not missing the global minimum. Then we also use a gradient descent method, which can be a lot faster if the problem is tractable, and if the data is informative enough about the parameters that we can find a unique solution. We also use MCMC, which is better at estimating the uncertainty. So it'll get to a local minimum and then explore around that area and give us a good estimate of the shape of the error structure. So we have those four methods, and we use those to generate a set of diverse solutions, and we pass them into a couple of genetic algorithms. So genetic algorithms thrive on having a lot of diverse, good solutions that they can kind of recombine and find the best solution to a problem. And so some of these, the NPGA is really good if there's a unique solution that exists with our data, and if there's some kind of trade-off that we need to explore, then the SPEA algorithm is a lot better, is what I found. So the result that we get will look something like this. So each of these represents one of our model runs, and so for any given Young's modulus and conductivity, the color represents how well we're fitting the pressure data. So just looking at the pressure data, it looks like it's a non-unique solution. So for any given Young's modulus, there's a conductivity that could explain the data pretty well. But if we look at tiltmeter data, it also has somewhat of a trade-off, but it's oriented in a different way. And so between the two of those, a lot of the models, the pressure data wasn't able to throw out. The tiltmeter data can show us we're incorrect. And so between the two of them, if we combine them into one estimate of the error, then we get a error structure that we can fit a statistical model to and get some estimate of what the parameter is and what the uncertainties are. And so looking at some of the results, so in this case I'm going to try to estimate the permeability, the Young's modulus, and the Poisson ratio of the formation using data taken from inside the formation. And I'm using different combinations of pressure data, tilt data, and the different components of strain data. And so if I just look at pressure and tilt data, we can get a pretty good estimate of the Young's modulus and conductivity and a pretty poor estimate of the Poisson ratio. So these error bars go all the way outside of the range of what's physically possible. So we're not really constraining Poisson ratio with that data. If we exchange the tilt meter for a vertical strain meter, then we get a pretty similar estimate of the Young's modulus and the conductivity and a better estimate of the Poisson ratio. If we use the pressure, tilt, and vertical strain, then we get a pretty similar estimate with Young's modulus and conductivity, maybe a little poorer estimate of the Poisson ratio. And if we use all three strain components, then we get a pretty similar result. But this is a 2D model, so when we go into 3D, we'd expect to get a lot more value from having multiple components of strain. And so this is just showing how we're fitting the data. So I ran 2,700 simulations, and I'm taking the 41 the Pareto optimal sets, the best solutions that we found so far. And so they all fit the data pretty well and are pretty similar to each other, even though they're coming from a pretty broad range of parameter values. So in the next case, we're looking at how the location of the instruments affects our estimates. So we're using data from inside the formation, and then also from in the upper cap rock, and from inside the injection well. So this is the data we saw in the last slide. This is how we're estimating the parameters on using formation data. And then if we use caprock data, we still get a pretty good estimate of the parameters, given that caprock measurements are a lot cheaper to make, because we don't have to drill nearly as far, and we don't have to have the risk of puncturing into the formation and releasing all the CO2 that we're trying to sequester. If we use data from the injection well, we get a pretty good estimate for Young's modulus and conductivity, and a really good estimate of the Poisson ratio, because that's where all the doming is happening, and so that process is a lot more sensitive to the Poisson ratio near the injection well. And if we use all of the data locations, we get a pretty good estimate for all three parameters. So in this next case, the forward model that I'm using to invert to try to solve for the data is the same, the three-layer system, but the forward model that I use to generate the data includes this heterogeneous layer. So it's like there's a layer there going on that we don't know is in our conceptual model, but it's polluting our data and affecting the way that we try to fit the data. So to do that, I'm using all of the different components of data because it's a tougher problem. And so when that layer is a high permeability zone, then we do a pretty good job of estimating the Young's modulus and the Poisson ratio. And we get pretty close to the effective permeability, given that it's a high permeability zone, but we have a much higher error. And if it's a low permeability zone, then we do a pretty good job of estimating all three parameters. Because in this case, a low permeability zone doesn't act as a blockage or anything. It doesn't really affect the flow paths as much. When it's a high permeability zone, then all the flow paths can kind of take a shortcut through there. And so this is showing how we're fitting the data. So we ran 2,700 simulations, and the 129 best solutions still don't fit the data very well. Some of them fit some of the data well, but no one solution can fit all the data well, which makes sense. So doesn't exist a parameter set that can explain the data that we measured because there's a conceptual model error. So, even when the data that we have isn't informative enough or when the conceptual model that we have isn't correct, we can still take the set of estimates that fit the data the least poorly and still get a pretty decent estimate of the parameters. And also, it notifies us that there is a conceptual model error and that we need to go back to our site assessment and look at what else could be going on in this area. So in conclusion, we can use geomechanical measurements to estimate the parameters of an aquifer, and we can use measurements from inside of the cap rock or inside of the injection well to estimate those parameters pretty well. And thank you.
All right, do we have some questions for the speaker? Let's see. I'd like to know, actually, is there a danger when you have something wrong with the conceptual model? Is there a danger with all of the associated error of, you said you could be alerted to the fact that your conceptual model is wrong. Could you also mistake that in the noise?
Yeah, I suppose if the noise is high enough, if there's some kind of process that's interfering with the data that you have, I guess that'd be more like conceptual model noise, though. Yeah. Yes.
Okay. All right.
Have you tried too mixing different alternate conceptual models in with your simple initial model, like you're saying, that may alert you that you have a problem with your conceptual model, but you're always going to have a problem with your conceptual model. So
that would be.
How about how would you think or apply that?
Yeah, for doing it in the field, I think we would have probably half a dozen different conceptual models that are all the different possibilities that we've seen from the geology and the wellbore data that we have, and then see which one is able to fit the data the best. Yeah.
All right. Well, thank you.
Awesome. Thank you.